move on to our next speaker. So this is Eleanor McHugh. Ellie's been probably using Go since the day it was born, I think, pretty much, and has a long and varied career in software engineering. She's done all sorts from mission critical avionics to digital identity work and banking security. And Ellie's also written a book which is called, what's your book called again, Ellie? I forgot the name of it now. I had it here a minute ago. What is the name of your book? What's the name of your book, Ellie? You need to unmute.
A Go Developer's Notebook.
Go Developer's Notebook, yes. Yes. I've written that down somewhere. I can't see where it is now. Yeah, the Go Developer's Notebook, which is a neat evolving tome, isn't it? It's a never ending.
It'll finish when I do.
Right.
That's actually a guarantee to anybody who buys a copy. I'm never writing another book on Go. It's this one and only this one.
It's this one, yes.
Your
exactly.
investment is well made, you see.
Brilliant. Well, we're looking forward to this talk. Ellie, this is Go for the Paranoid Network Programmer. And I'll leave it to you to share your screen and do whatever you need to do.
The bit I hate. So
yes.
Here we go.
How do you want people to handle questions? I mean, do you want me to interrupt you if someone writes a question in the chat, or do you want to wait to the end?
Yeah, if anybody's got a question and it looks interesting, just interrupt me.
Okay.
I am capable of thinking of two things at the same time. Otherwise, I'd never be able to give talks because I make them up as I go. So, come on, Scare. Oh, I need you to give me permissions to share screen.
Okay. I thought maybe that had been done already. Are you a host? You're a co-host. You should be able to do that now.
Oh, I wonder which of my. Yes, that's the one. People, there we are. People should allow Zoom to share your screen. Oh God, us strikes big, sir. I seem to spend half my life telling it, yes, you can do this thing that I have asked you to do. You stop, ask permissions on everything. Right. And that means I will be back in a second because I have to quit Zoom and come back.
No problem. We'll see you in a sec.
Come on. This is the point where you're now supposed to quit. I've clicked on quit. Can anybody actually see my screen?
No, I can't.
Let's try that again.
Yes, we can see your screen now.
You can see the wrong screen, but it's
you see a screen.
The starting point. So let's come. Stop sharing. Okay. And that's the one I actually want to share. There we are.
Beautiful. There we go.
There's the Odyssey slides. Okay.
Fantastic. Right. I will be quiet now. I'll let you get on with it, Eleanor. Okay. See you on the other side or halfway through if anyone's got questions.
I haven't given this talk in a while. So I will be making this up as I go. It's all properly laid out so that even an idiot like me should be able to get this right. And as you can see, it's now with added WebSockets, because once you've seen WebSockets, you might never want to do any of the rest of it. So here goes. So this is me. I have a book. The book is a living book, which means you can't buy a physical copy, only an ebook, and you buy it for life, one-time purchase. That's my thingy. This talk touches on several topics that each and every one of them is fraught with possible insanity. Networking, when you get down to a low level, can be very frustrating, trying to find out why things aren't going wrong when you first write them. Concurrency is intrinsically nuts, even in Go it has its problems. And cryptography is just, I'm not a cryptographer, so only take what I say with a pinch of salt. That's the legal disclaimer that my business partner, who is a cryptographer, insists I always put in at the start of talks. So we're going to start off with the basics. We're going to start off with serving some HTTP. So HTTP serving in Go is dead simple. And in fact, you saw a nice example of it there in Matthew's talk. We've got a package for it. We have a whole pile of complicated infrastructure inside the net HTTP package, if you want it, to set up very specialist custom web servers. But by default, it gives you a boring average web server that you can just attach things to that you want to serve. In this particular case, I'm going to try and keep all of my examples to just doing hello world, on the grounds that then I don't have to handle any text handling or anything like that. If we have time at the end, I will actually show you an example of a chat client and server written with WebSockets in just Go. Well, bits of it in Go. We'll get there. We might not. But anyway, so in this case, I want to serve up a function that all it's going to do is print out whatever parameter I happen to have given when I set up the handler. And I want it to serve on the route /hello. I'm going to have to ask my HTTP server to actually listen and serve something. And that's actually going to create a port 80 that other people from outside my box can get into. There's not a lot exciting going on here. The message is a constant hello world. The address is a constant 1024. You'll notice that if you only want to reference a port on the machine you're currently on, you don't have to give the domain name. You don't have to say localhost. You don't have to say 127.0.0.1 or any of that. You just have to give it the port number, and that's quite nice actually. I build a lot of software that involves running up dozens of microservices all on the same machine communicating with each other, and it's just quite handy when writing bash scripts if I can just chuck a number in and then have it auto incrementing the thing rather than having to composite a whole domain name or something. The main other thing to notice here, so HTTP handle funcs, they take a function that's got two parameters. One is a response writer, and that's based off of a standard IO writer. So any method that you could use with an IO writer, you can use with a response writer. So for example, here I've used fprintf. And you'll notice also that I've imported funct into the local namespace because I can't be bothered to type funct all over the place. And I'm trying to get out of this nasty habit because people keep telling me off, but I've been doing it for 11 years. So it might take a while. The other thing that a response handler has to take is it has to actually take a HTTP request object. And this has got everything you need to know about the request that's just come into you as seen by the server. So if you want to get at the headers or anything at all, they're all lurking in there to be dug out. I'm being quite polite here, and I'm setting a content type of text/plain. You don't have to set a content type, but obviously if you're talking to most modern web servers, they get a bit upset if you don't point out that something is application/JavaScript or whatever. So now there's probably quite a lot of that broken apart. I've imported NetHTTP into the same namespace because it actually makes the example easier on the eye, now that we know where these things live, and it's not a lot of code. So boop, 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 nothing now I want to talk about. Oops, I've done an abstraction. Oh yes. So the great thing about Go, of course, is that we do have closures. We do have inline functions. Functions can be first-class values. So you can just as easily, if you like, when you define a handle func, actually define its handler inline. I tend to do that an awful lot, and there's swings and roundabouts. The advantage of it is if you want the actual route you're handling to be configurable at runtime, you want to be able to pass in several possible different handlers, then it's a parameter. You just pass it in, and it's quite nice. But it does mean having to know where to look in the code for where your closure was. And closures can do odd things because obviously they close over state that's outside the handle func. So if you accidentally make it dependent on something that might also be running somewhere else concurrently, that can be bad. And under the hood, the HTTP web servers are actually running concurrently. They run each time the handler is accessed by something coming in on port 80, it will be running its own separate Go routine. So it's always best to just remember not to pass state into them that you shouldn't. Anyway, let's skip past that. That's boom, gone. Right, HTTPS is not actually that much more work. And this is kind of nice, really, that it's not that much more work. We have a slightly different function for doing it. So a listen and serve TLS. And for this, we've still got an address that we're serving on, but now we've also going to give it a certificate and a key. And the cert is going to be the cert that's actually going to be used for it to be seen by other servers. And if I remember right, the key is to unlock the certificate. Do not quote me on that, because I'm looking at this off the top of my head, having just done dinner for my child. So I'm not in full tech space right now. There really isn't anything else, though, to handling HTTPS. This means that if you want to, you can actually handle both HTTP and HTTPS in a relatively small piece of code. So here in this example, which incidentally is the cover of my book, because it's quite fun being able to say to people, hi, by the way, this is how you run up a pair of web servers. What we've got going on here is we've got two concurrent routines, effectively. We've got the one that's running in the background doing listen and serve on port 1024 in this case, but it's listening for standard HTTP traffic. And then we've got another one that's listening on port 1025 that's listening for TLS traffic. So anything that would normally be port 443. I've plumbed in a little bit of concurrency tie together here. This make channel of bool that is assigned to done. This is just so that if listen and serve TLS ends before listen and serve ends, it won't end the program, because the moment you fall out of main, the program will end and it will shut down any Go routines that are still going in the background. And so I'm using that channel effectively to create a synchronous block at the end that says, fine, if you get here because you've stopped serving TLS, at least hang here and serve standard web content until such time as the standard web server port shuts. Okay, now it's not a very good solution. It's a highly fallible solution, but it happens to be one that fits quite nicely as a first example of, oh, look, I can use a channel to guard to make sure that two things both complete before I end the program. Obviously, when I wrote this, I was expecting to belabor this point quite a bit. Now, what I can actually do is I can write my own little wrapper for that concept, which I'm calling Spawn. And Spawn is just going to take a bunch of Go routines or functions that you want to run as Go routines, and it's going to chuck them off and it's going to execute them. And in this case, I can do it individually or together, and I'm going to show you the code for Spawn that does this. So, all right, so Spawn takes a variadic parameter. So you can pass in as many functions as you want. And they're all functions that don't take parameters, which is basically just the simplest way to say, fine, pass me something that can be executed. And then it's going to go off and it's going to range through all of these. There's a channel in there. And that channel is going to make sure that everything that is launched completes. Now, the reason that this works up here is that both of these spawn functions will spawn stuff off and then complete and leave, and they'll run. But I think there's a bug there. I think they'll run subsequent to each other, but they'll they'll guard any traffic that's in them. So the moment you start thinking about writing your own concurrency primitives, you are running into trouble. Concurrency primitives take a lot of thinking about, and they're often quite simple looking bits of code. And you'd be amazed how often you look at something and you cannot see what's wrong with it for hours because it's 5 or 6 lines of code and it's one very simple conceptual problem in there. So there's a better way of doing it than this. But what you can notice is it is possible to prune the code in this spawn down. This for trick at the end, this is awful. This is bad code. Do not do it, because it's going to run through that and it's going to keep taking things off of that done channel. And that's going to be difficult to think about. So I'm going to skip past that because it's awful code. It's really just there to make people's heads hurt and set up the fact that we actually have a nice solution in the standard library already for dealing with this idea that I want to run several things at the same time. And I want to make sure that they, oops, that they all come out clean at the right time. So that's a wait group. Now, where to start? All right, so wait groups. Firstly, we're going to have this simple function. This handler literally does nothing. It accepts a request from a web client, and it literally returns nothing. It does nothing. It just successfully opens and shuts a connection with that web client, right? It's the bare minimum that you can possibly do in the way of a network program. Most people would look at that and go, there's no code in the body of it, so it's no use. But actually, every time it hits, you've effectively just created a signal. And if you wanted, you can. So to go back to the example that the examples that Matthew was using, he had effectively what was the way that Jaeger was working was effectively introducing a middleware in which what you were actually handling was handled inside the handler that was that it's specified. That if you put this inside that, this would produce telemetry. It just wouldn't do anything. It's a no-op for the web. Now, we'll go through this a little bit slowly. Firstly, the wait group concept lives in the sync package. And here I'm just going to say, here's a sync group. I'm going to call it servers. It's not a very good name for it, but it will do. Every time I launch something, I am going to add one to servers. I'm going to increment the count. And every time that thing completes, oops, come back. Every time that thing completes, it's going to call done on servers as part of its deferred exit routine. And when it does that, it will synchronously bring down that value. I don't have to care about the internal details of how wait groups are implemented. I can therefore have two separate Go routines, both running, each of which will quite happily say when it has finished. And then this call at the end, servers.wait, that will just wait until all of the servers that are executing have all completed. So it makes for a very nice little coding pattern. You can build other things on top of it as well. So let's see what we're doing here. So down here, I've reintroduced my idea of doing a spawn function that's going to do something related to launching off a separate Go routine that will play nicely with servers. And now my spawn will add to servers. Now, this is not a nice piece of code because for one thing, I'm using a global variable for servers. And so it's now specific to this particular program, or somebody has to define that global variable in their program if they want to use this in a library. That's not a very nice way to do things. So I would abstract that out. In fact, I'm surprised that I didn't, because normally I'm obsessive about that. What I would actually probably do is actually make either define a type that had this spawn method that itself was a wrapper for a wait group, or I'd pass in the particular wait group variable as the first parameter of spawn. But the point is, it cleans up the code that you would then use, and it then allows you to share several different executions of that concept across just this one wait group if you want to. So now you can, in several different places, use it, but you're always going to be hanging on the same core variable that's going to hold the program open at the end of the main function. Anyway, it's not a very good example, but it's a great way of showing off wait groups, but you can use what they're for. So TCP server. See, HTTP lives on top of TCP. TCP lives on top of IP, which is the actual underlying internet protocol. There's another thing called UDP that lives at the same level as TCP. And the difference is TCP is a transmission protocol. It has error correction and it knows how to spot if the connection has lost packets. And UDP isn't. UDP is just a straight datagram sender. And it will, if it loses packets, your application has to figure that out, not the actual control layer. And in the modern world, very few people write TCP servers or write UDP servers. These are the things you write because you're writing, you want to do real-time chat clients and things like that, and you're using client software rather than using web software. So there's a good reason why people don't actually write TCP servers that much if they can avoid it, and that is that it's an awful faff. You know, with a standard HTTP connection, You send in your request, your server does some processing, it sends back a response. And all right, that doesn't have the back and forth real-time feel, but it's a bounded problem. It's easy to get your head around. With TCP, you spend an awful lot of time asking yourself, I wonder what the packets on the wire look like, because you're having to care about individual packets. And there's a lot of faff in getting it up and running. So to open a TCP socket, firstly, all of this lives in, the TCP stuff lives in the standard net package. And being a server is actually quite easy. All I have to do is just listen with the TCP protocol on port 1024 in this example. And once I'm listening, I need a nice little acceptor, a listener, that will quite happily then, whenever it accepts a connection in, will then do some work. And that's simple enough. That implies that we're going to have either an infinite loop, or we're going to have a loop that's going to be testing on an error condition to see if our actual listening socket is broken and needs to be restarted. In this case, it's an infinite loop. I have done very little error handling in this slide deck because it doesn't. It helps with real world code. It doesn't help with seeing the patterns, because you end up with so much error handling code if you're not careful. So in this case, when I accept a connection in, I'm going to launch my own separate Go routine. This Go routine is going to have access to the actual underlying net connection that I'm listening, that I've actually accepted on. Because every time I accept, even though I'm listening on one particular port, every time I accept a connection, I'm actually getting a totally different connection. I can have several of them open at a time. This is why TCP is so good. If I want, I can have 10,000, 100,000 in theory of them open on the one box. That doesn't actually often work very well, but I can. And they're all advertised through the same port, but the actual ports that will be, the actual sockets that will be communicated over will be different once that connection is in place. Because I'm launching this in a Go routine, I'm going to actually manually pass it in the connection that I have received. Now, the reason for doing this isn't really, in this bit of code, it doesn't really matter. In this bit of code, my Go routine that I'm closing over is happening inside that if statement. There's probably enough gap between separate incoming connections on my TCP port that I won't get another one come in before that Go routine is launched. But one of the single biggest trippers with concurrency in Go is that if you put launch Go routines inside a tight loop, the loop will probably have executed many iterations of itself before the very first Go routine you launch has actually been scheduled by the scheduler. Meaning that if it's dependent on closed over values from outside the Go routine, they won't be the ones that you were at the right point in the loop for. They'll be the ones for the point the loop is now at, and those will not be what you expect. And this can, the first time I ran into this, I spent about 4 or 5 days trying to debug it. I mean, this was really back very early in the days of Go, and most people weren't doing the kind of things that I was doing at the time. And it was only when somebody in the Go team looked at it that they could go, well, this is what you've done. And at that point I thought, well, I'm an idiot, followed by, why isn't there a FAQ on this? Because it's so easy to make this particular mistake. But in this case, it probably doesn't matter because of the slow latency on accept picking up the next incoming connection. But it's still best practice to do this sort of thing. And I don't use that phrase best practice often, but this is one of those few places where I really think it matters. So we've got that off in its infinite loop doing its job. We can abstract a certain amount of that out as just a listen function. And to be honest, I really wish that it was just abstracted out in the net package as a listen function, because the boilerplate, there's not a huge amount of it, but there's enough of it that's annoying when you keep writing it. So all I've done here is I've introduced this idea of a function that can take a handler for a network connection, much the same way that a handle func takes a handler for a web connection. And then I've just put all the boilerplate for actually setting up listeners and then running that function against multiple incoming connections. It's not very exciting code. It's just, but it means that in the main listen function that main's calling, there's a lot less that actually has that you're looking at. You know you're listening on for TCP on port 1024, and on any connection that comes in, you're going to want to close it when you exit the handler, and you're going to want to print out hello world. And now my main concern when I'm looking at main is actually right there in what I'm doing, not down here in all of this stuff that's for doing it. So let's get past that. Okay, TCP is a client-server protocol. This means you write TCP servers and they handle connections coming in from TCP clients. So in this case, first off, as a client, I need to be able to connect to a server, and the net package gives us a dial function that allows us to do that. So in this case, I'm dialing a TCP connection on port 1024 of my local host. It's obviously good practice to actually call close on a connection when you're finished with it. I'm going to use buffered IO to create a reader. Now, the connection itself acts as an IO object. So therefore, I can use anything that can take an IO reader or an IO writer to interact with that connection stream. I've used BuffIO's new reader here because that will create me a buffered reader, and then I can use read string and just lift out an entire string that's, in this case, end of line delimited. And that's a lot nicer than passing around byte buffers and caring about how many bytes have been read in and checking on whether or not bytes have been done. There's an awful lot of plumbing in the for IO readers and writers and read writers and so on throughout the Go standard library. And whenever you can possibly use it to achieve what you want to, use it. Do not write low-level byte handlers if you don't have to. It's just a horrible code that you'll end up writing. It's prone to problems. People write stupid code with buffer overruns in that you're never going to get if you use any of the standard library facilities. And you're saving yourself a huge amount of nightmare in the long term. So let's see. So I can abstract out all of that dial code somewhat, and yet again leave myself a nice simple code pattern in which I've got this connection handler that in my particular case, I know what I want to do is read a string. And if that string isn't blank, I want to print it out. So I've now got a client and a server. The server will serve hello world. The client will just read hello world and print it. So boom, boom. Is there anything there? No, I was overdoing it. Yeah, let's cut that way. Okay. The internet is not a very secure place, I think is the summary. For the first few years, well, for the first couple of decades that I had access to networks, for many use cases, you could get by with using TCP and UDP or plain HTTP. An awful lot of the traffic that was going backwards and forwards, it really didn't matter if it was secured. And I mean, even today, there's reasons why you want to put up stuff that isn't secured. But anything you're handling for people, anything that's got privacy implications, you need to be using a secure transport layer. The standard secure transport layer is TLS, and Go supports TLS out of the box for HTTP and for TLS. The main thing that matters with TLS is you need a cert, a certificate, which are normally stored in PEM files, and there are functions for reading all of those in. There are also functions in the standard library for both checking server-side certificates if you're a client, but also checking client-side certificates if you're a server. Now, very few people actually use client-side certificates, and that's because a variety of reasons, many of them to do with a lot of people writing things that they just don't think that way. There's also something of an enterprise. There were bum fights in enterprise culture. It's not really my area to talk about, but my business partner, who has been doing PKI since the late 90s, that's public key infrastructures, he has long rants on the subject. getting people to use client certificates is really difficult. If you have certificates, you can pin things very effectively, because you can say, well, I don't care, you're only allowed to come in from this address, and by the way, you've got to have such and such a certificate. Or you can be rather looser, and you can say, well, if you've got the cert, I'll let you in, even if you're from an address range I don't recognize. So it gives you some control over which clients are allowed to talk to you. And obviously, server side, if you want to be serving content that people coming to you believe, you need to have a valid certificate. You know, you can get by with self-signed, and Ghost Net Package will allow you to use self-signed certificates, because it allows you the choice over whether or not you want to validate certificates when you actually check them, i.e. validate that they are against a known trusted CA. And to be honest, I mean, I use self-signed certificates for a number of purposes, and I use signed certificates for others. But in the modern world, we have Let's Encrypt. So with Let's Encrypt, you can always have a valid signed certificate for any purpose if you want to, just by going along to them, getting a copy of certbot, and just making sure you have a cert, or as many as you need for the purposes you want. So anyway, let's have a look at some code. That's my ranting over for the moment. All right, with TLS, we've got a fairly similar setup as we've got with standard TCP. We've got a listen function, and that's listening. In this case, I'm listening on a port 1025, and I'm going to take a handler just like I did previously. But there's a little bit more work I need to do. So I need to configure a TLS certificate. So in this case, I've got a cert and a key, because my certificate is encrypted. It doesn't have to be. You can use unencrypted certificates if you want to. There are swings and roundabouts on that depending on your purpose. And this is not a crypto talk, so I'm not going into that. But anyway, when I configure up my TLS connection, the first thing I've got to do is I've actually got to load in my X509 key pair that lives inside the cert. That's the public key and the private key. Okay. And obviously I give it my cert, I give it a key, so it can actually unlock my file. And out of that, it will give me a valid certificate that I can then serve. Configuring TLS, well, in this case, I'm configuring it so it's got a set of certificates, and I'm only giving it one certificate. That's my certificate. I could give it multiple certificates if I wanted. And that's how we go about building certificate chains and so forth. I also need to give it a source of randomness, a source of cryptographic randomness. So rand.reader should do the job for me, at least as well as I need it here. Go has the advantage of it has a clean room, well, an advantage and a disadvantage at the same time. It has a clean room crypto implementation by Adam Langley of OpenSSL fame. It's efficient, it's clean, its API is mostly a nice API to use. It lacks an awful lot of things that OpenSSL has, but as most people don't use them because they are incredibly error prone to use, it's actually a very nice implementation. And as much as I would say you can rely on a crypto library, you can rely on Go's crypto library. Disclaimers apply. I'm not responsible if your app that you write using this kind of code and Go's crypto library gets hacked, and so on and so forth, yada, yada, yada. Having set up our connection, our listener really, it's just the same thing. I mean, look at it. It's literally just the same code we had before, but with the addition that we now give it a TLS configuration. So that any incoming connection will be recognized as either having TLS capability, doing the handshake, and then I send down the cert so that I'm proving my identity for some given value of identity, or it won't, in which case I won't talk to it anyway because it's not actually trying to do a TLS handshake. So boom, boom, go past that. That's very interesting at that point. And I was belaboring something which I can't remember why now because I wrote that 4 years ago. So, oh, it was a bit at the end. What was that bit at the end? Oh yeah, I mean, all I did did there was just write an extra little bit of wrapper that given a connection and a function to run on it, will allow you to put some handler boilerplate in. So in this case, it happens to be doing the automatic close on the connection. There might well be a lot of things you might want to do in there, depending on what your application is doing. There might be a lot of state you want to clear up when you shut down a connection. Or there might be database queries you either want to perform or database queries you want to expunge. Because obviously if your point is to be private in whatever it is you're doing over a TLS connection, you then have to also make sure that you do proper cleanup so that you don't leave evidence of what the connection was doing. And that's caveated by the fact everybody now has laws about what you do have to maintain, unfortunately. The client side of doing a TCP TLS connection is not much different either. Yet again, we need to actually configure TLS so we've got a key. And so we've got a certificate. Only in this case, we're now client side. And you'll notice that when we come down here, the main difference is I've introduced this particular property to the TLS configuration. Insecure skip verify. Now, by default, that's set to false. By default, Go wants you to use client-side certificates. And I highly applaud of that. I can't think of any other TLS library on the planet that says by default you should use client-side certificates. I think it's a really nice thing, and I do hope that people are really doing it. But I will admit, in about 80% of all the code that I write using TLS, I end up setting that to false. So apart from that, yeah, there's nothing else really to say there. That's all the same code. Oh, well, I mean, we've got a dial function as well. And the dial function is pretty much the same as we had with standard TCP. It's just now we have to pass in a TLS configuration as part of doing our dial. And that's that. So it's not very exciting. Right, UDP. UDP is really very, very different to TCP. It's a point-to-point protocol. It's you fire raw datagrams at some target address, and there isn't a concept of a client and a server. However, it's quite difficult to write programs without thinking of one person as listening and another person as sending. So I've broken UDP into two parts here: how to serve UDP, how to respond to an incoming request. And then the other half is how to actually listen to UDP, how to actually be a requester rather than a requestee, rather than a server. So, and there's quite, we'll skip through this. I'm sure most of this will be dull boilerplate. When I first wrote this slide deck, the reason, this is actually the third iteration of it. It's acquired new things over the years. And today it's acquired WebSocket stuff. The reason it exists is there literally wasn't, at the time I wrote the first version of it, any one source you could go to and see how to do network comms in Go, which seems really weird because, I mean, Go is a really good language for that. But in this particular case, so serving out UDP content. Firstly, we're going to want to listen for some kind of incoming datagram. We're not listening for a connection anymore. We're no longer listening for a socket that's going to be a permanent connection or a semi-permanent connection between two ends. We're just listening for datagrams. So that hit a particular port on our server. So God knows what's in the datagram. It either makes sense to us because it's intended for us by somebody who knows what we're actually looking for, or it's any old garbage that somebody decided to shoot at our port. And that's a very different, that's different to TCP. With TCP, the stack has already filtered out all of the crap. I don't see crap. I only see stuff that actually looks like TCP connection requests. So in this particular case, I'm going to listen on port 1024 again. And I've got this rather complicated function signature here where I've got a network UDP connection. I've got a network UDP address, and also I've got a byte buffer. So if we skip down and we look, we'll come back to that in a second. Boom, boom, boom. Cool. I was definitely thinking in a different direction that day. So, all right. The first thing we need to do is we need to actually resolve the UDP address that we've been given as a UDP address. And that's actually, if it works, it's going to give us an address that we can talk back to, because when we serve, we're actually receiving content and we're going to give it back. So we want to give it back to an address that makes sense. And then we're going to listen for UDP. We're just going to sit there and we're going to say, we're going to sit on this address and we're just going to listen for UDP packets. When we get a packet coming, now here I'm using a byte buffer, which I'm making a 1024 byte buffer. This is why this kind of communication is fraught. I'm going to be lifting raw bytes out of the network buffer. And then I'm responsible for making sure I do sensible things with them. In this particular case, every single time through, I'm making a fresh buffer. And the reason I'm doing that is so that I don't have a buffer left over from a previous incoming message that could be used for an overrun, or could be used to extract some data from the previous call, or some other nefarious reason that I can't, as the coder writing this code, be certain won't happen. After all, Go is a safe language by default, but on the other hand, you can do some pretty vicious stuff if you happen to use the unsafe package. And if you tie that together with reflection of the network stack, you can really do some horrible things, especially if you want a box where somebody's kicked your network card into promiscuous mode, so that you can actually get into the raw byte, the actual raw buffer underneath. So I'm making sure that I'm not reusing buffers. I'm going to have fresh buffers every single time, and the garbage collector can take care of that. I'm not bothered about it. Once I've actually set up my buffer and I've done a read, I'm also then going to run whatever handler I've got for that incoming message in a separate Go routine. And you'll notice that that's where I actually use that function with the complicated signature. All of this code is online, and it's the sort of code you want to sit and you want to read. Listening to a description of it is only superficially useful, unfortunately. I've decided to tidy up a lot of the boilerplate there as this concept of serve UDP. And you'll notice that takes care of the setting up the byte buffers, doing the reading of UDP into one of the byte buffers off of the actual connection, and then launching the handler. So we can say goodbye to all of that. I mean, it does what it does. And then if we go back to what our actual purpose is, that's also we can write to that out on that UDP collection, hello world, to the address that we've got. So boom, 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 boom. We skip past all of that. Boom. Now, UDP is peer-to-peer. So I can actually serve and I can request in the same piece of software if I want to. But I've got two very different code patterns for doing it. I've got the one that is the listen, and I've got the one that is the dial. So in this case, I'm going to dial out on port 1024. And I have set up this dial function to take care of all the boring boilerplate of resolving an address for UDP purposes, and taking a connection I want to handle. So dial, I really think that dial or something like it ought to be in the standard net package, just because this is boilerplate that is just annoying to keep writing. So what is our actual payload doing? What are we actually doing when we send our UDP request out, hoping to get some kind of response back? And bearing in mind, when you send UDP traffic, you don't necessarily get a response either. Just because I say, please send me a response, does not mean anything at the other end will ever listen or ever respond. But in this particular case, I've decided I'm going to write out something that is delimited by a carriage return. And in this case, it literally is just a carriage return that I'm sending. And then I'm going to read back whatever I get, which will be carriage return delimited, and I will print it out. So if we go back and look in our server again, what we were sending was this byte buffer with hello world in. That's the response. And down here, what we were triggering on, we weren't even checking to see what kind of what actual data was coming in. If you look at the gray line there, that's not underneath the red one. I might actually be able to, because I'm not in thingy, I can actually probably highlight that. If you look at, oops, no, can't do it that way. If I come down here, if you look at this line, I'm reading from UDP into that byte buffer, But actually, that's not checking to see what's been read or any content. It's just checking to make sure there wasn't an error happen. So actually, I'm literally just waiting for any kind of successful packet arrival. If a datagram arrives at this server, I will send back to wherever that datagram came from the response, hello world, whether it expects it or not. So if somebody pings me on that port, their ICOMP request is going to get hello world back and whatever and so forth. There's literally no real rules in the UDP world. I mean, it's not a land for protocols in the conventional sense. All right. This is not a talk on crypto, but it wouldn't make much sense to do this talk on crypto and do this talk without some crypto, because I can then show you some crypto in the context of doing networking that's separate from using TLS. TLS is what you should use off the shelf if you want to do any kind of network transport, but TLS is not your only option. And there are reasons why sometimes you might want to do your own crypto over TCP connection, over UDP connection, or even over HTTP connection. So I'm going to go through a little bit here of how you do AES crypto, and I will speed up. I think I've also, what else have we got? We've got AES encrypt and decrypt. So let's shrink these out the way. And we've also got RSA encrypt and decrypt. And I have loads of code online and many talks in which I've gone through this. So you can check this out very easily if you don't follow anything that I say, which you probably won't. Right? Because I find this one of the most difficult things to talk about at times. All right, let us imagine that we have a program in which we want to listen on a port. And when we receive a connection on that port, we would like to send an encrypted response. And the thing about AES encryption is it's symmetric key. So both parties have to have the key. There's no way for getting, it's not like public-private keys. So with public key crypto, you give me a public key that anybody can have, that they can talk to you on, but you're the only one who can decrypt because you're the only one with the private key. With symmetric crypto, we both have to have a copy of the key that's used to encrypt and decrypt. It's one key and it does both. Now that sounds like an awful idea, and everybody who ever sits through a basic crypto course will be absolutely blown away by diagrams of Alice and Bob communicating using public-private key pairs and Diffie-Hellman key transport and all of that. And they'll go, that's amazing. I need never leak key again. But the trouble is public key crypto is much weaker, as in it takes many more bits in the key to have the same strength of encryption for the content that's going to go over the wire. Whereas symmetric key crypto, as long as you keep transporting the keys is a nightmare, but the keys themselves are much more powerful. So with here I'm using AES 128. 1, 2, 3, 4, yeah, 16. I've got 16 bytes effectively in my key. And obviously I've used a numeric string here because it's easier on the eye. But, you know, each one of those can be any one of 256 values between 1 and 255 rather than a digit. That's a very dense amount of encryption data. And there are lots of things I can then do with it. Whereas with public key, I'd be looking to get similar strength at probably something like, I think to AES 128, I'd probably be looking for at least a 2 kilobyte long key to have equivalent strength against brute force cracking methods. So that's why the two types of encryption both get used. Symmetric is easier to understand. Public-private key is how we transport symmetric keys, because it can be very strong for very small chunks of data. All right, so in this case, I've got a handler, I've got a listener. We've seen that before. That's not very exciting. And I'm going to introduce an encrypt method that's going to take hello world, my message, and it's going to encrypt it with my key. And then I'm going to write it out on the UDP port. My listen and serve UDP methods, which will get used in this, are exactly the same as we used in the UDP serve example. So no need to repeat that. Now, my encryption method. So everything to do with AES lives in crypto/AES, the crypto AES package. But we also need to make use of the crypto cipher package. And we'll see I mean, the reason we need to use it here is because AES is one example of a cipher, and we're going to use code from the cipher package that can work with any cipher, that all of the different particular ciphers are written to interoperate with. So in this case, I've got a couple of things I need to do. I need to have a padded buffer. I need a buffer of the same length as the length of my key, or a multiple of it, because otherwise it's not going to encrypt with AES particularly well. Padded buffer is dull. It's just it'll just find out what the block size of a buffer is, and if my message isn't long enough, it will create a byte slice that is long enough. And for a real world problem, you wouldn't pad with null. What you would do is you would pad with random data. And there's other stuff that I don't think we get into in this talk that you can do on top of that. But anyway, the point is I want to create an encrypted chunk of stuff. And my encrypted chunk of stuff, I'm then going to encrypt using AES.newCipher. That's going to give me a cipher from the key that I can then use to go off and actually encrypt my padded buffer. So if we go down here, crypt blocks, boop, boop, boop. Have I literally got to? No. Yeah. Oh, well. Right, my encrypted stuff is going to come back as a slice of bytes, because it's going to go straight onto the network anyway, so there's no point in sending it back as a string. And in this particular case, I'm going to create a necessarily sized byte buffer that's going to be able to take the block size and also the length of the message. Now, the reason for this is I can't just send the message encrypted. I need to send something called a nonce. This is a piece of random data that's of the same size, same number of bytes as the block size of the cipher. So for this, it'll be 16 bytes. And that actually randomizes this particular message in a manner that I, the sender, and you, the reader, can cope with, but ensures that somebody else who doesn't know what that nonce is, even if they've got the key, isn't going to be able to read my message. So the nonce traditionally is considered something we can pass around as plain text. I've been trying to find out the answer to why for 11 years. I still don't. Actually, I've been trying to find out the answer to why for 16 years now, thinking about it. Nobody's ever given me a good answer. But I think it's the fact you use them once. And there is a bit of there's a bit of information theory around one-time pads that basically says if you only ever use a key and a message together once, and you only ever send a message once, no one will ever crack your message. So I think it's related to that. This nonce is traditionally in AES parlance called an IV, an initialization vector. So it's not very exciting. We just read 16 bytes of data from a random source, put it in a byte slice, and use it. And then we just do a bit of encryption. That's not very exciting. Decryption is the next bit. So for decryption, I need to have the key. I can't decrypt if I don't have the key. Even if in my 16 bytes I've got one bit out of those 16 bytes wrong, I'm not reading the message. It's just not happening. I'm going to have this function I'm going to explain in a minute called request message. And in this, I'm going to have a handler that basically will receive a slice of bytes and will do a decrypt on it using the key. And we can skip past that. So request message is not very exciting. It's basically boilerplate that will, boom, connect to our server with just a carriage return. Actually, even this carriage return isn't necessary. You can do this in such a way that you literally you don't write anything to the server, but the connection still effectively happens. So you'll still end up getting a response. But having the carriage return in there makes it a little bit clearer that we are sending something. I've got to have a buffer that my message is going to have to be written into when I receive it. I read that message off of the connection. And then what I'm going to do, what I'm interested in is actually lifting out the message itself, which obviously goes from 16 bytes in. I'm not interested in reading the random bit at the front. Sometimes I wonder what I was doing when I was writing particular code examples, because if I wrote this now, I'd write it very differently. And it's like the worst person you can ever try and read code from is your own old self. But anyway, our decrypt method basically runs more or less the same as an encrypt method does. It's just now we have to unpack some stuff. We have to unpack our message to get out our IV and to get out the actual content. And then we have to do set up a decryptor that now has that initialization vector in. And then it will run the decrypt and we'll end up with yet again a byte slice, and that byte slice will be the same as the one that came in. And our unpack method is really very dull, and it's just taking advantage of a couple of neat tricks in Go. The fact that obviously I can return multiple values, and the fact that I don't have to give the start index of a slice or the end index of a slice if I'm working all the way from the start to a point or from a point to the end. So skip past that. So, let's see. Yes, so RSA encrypt. Right, we use RSA for public-private key, and we use that so that we can transport our symmetric keys. We never use RSA to transfer messages. It's important to stress this because I'm about to use RSA to transfer a message, but it just isn't strong enough for any real-world case. For one thing, with AES, you've got things like blockchaining modes, where there are ways of setting up a sequence of encryption across multiple blocks. That means that if you pick up the second block, you won't be able to decrypt the third. You've still got to have the first block and the key to get the whole message stream. And there's a whole pile of there's stream ciphers, there's block ciphers, a whole pile of stuff that's quite cleverly devised infrastructure that lives on top of the standard AES algorithm. And then there were packing modes that allow you to repack a packet of data for transmission, so that both ends, then it's scrambled and then descrambled before you look at it and so forth. None of that stuff exists with RSA. RSA is a pretty dumb mechanism. It's like, hi, I've got a 1024-bit key. I can carry a 1024-bit message. I've got a 2048-bit key. I can carry a 2048-bit message. You know, there's actual hardware that you can get to accelerate all of this stuff if you're ever actually doing this on a really high load server called a HSM, a hardware security module. And the state of the art in hardware security modules for public key crypto is still 2K keys. Even though I don't have a single thing I use on a box of mine at home, or that we put in any kind of designs that we do commercially, that's less than 4K, and I've used 8K keys in the past, which is a nightmare because it's like 8 bloody kilobytes to carry around. There, you know, this is the really, there be dragons here just by using this thing. Do not use this badly. So I'm now going to break all of those rules, and I'm going to send the message hello world using RSA because it's the easiest way to demonstrate how the algorithms work. So firstly, I've got a listen function, and inside it, I've got the concept of an RSA public key. And I'm going to then set up this beautiful thing. There was a time when I thought that the Go binary encoding was very useful, because obviously if two programs happen to be running the same particular release of Go, and they've both got the same description, the same binary description for struct or whatever, they can talk to each other directly very efficiently. And then it's just on both sides to actually have the correct types defined inside their respective programs to be able to make use of those types internally rather than as anonymous types. And that seems quite persuasive, but I must admit, in the last couple of years, the more time I've spent playing around with some rather odd use cases on the web, the more I've actually become a bit of a fan of JSON format, even though I loathe and detest JavaScript. So, but GOB basically, even sounds horrible when you say it, but GOB allows you to basically take any binary data that you've got inside a Go program and turn it into a form that can be squirted over the network. Now, in this case, I'm going to say, I have received some binary data from someone who is running a Go program, and I would like to decode that into a buffer B which is going to be created out of the standard byte stop buffer. So it's got all of the boilerplate method, all of the functions for that. And then I am going to decode that using into my RSA key. So please send me your RSA public key is what I'm basically saying from a Go program, and I will then store it into my public key variable in my Go program. And it sounds much easier in English than it does reading it, actually. And then I'm going to use that public key to encrypt the word, the message hello world, which is a slice of bytes with hello world in. And I'm going to add an RSA label. Now, an RSA label sort of does the same job that an IV does with AES. It provides something that distinguishes out that particular response. And both client and server need to know the RSA label. Right, so in this case, once I've encrypted it up, I've now got a message that I can write straight to UDP. It's encrypted with RSA. That's actually really easy to do. We've now got an RSA encrypted message that we can squirt over the network. And as long as we use a key that's long enough, so our message is 11 bytes. So we need to use an RSA key that's at least 11 bytes. Now, this is the fascinating thing. I can use an 11-byte key in RSA because it's not on fixed block sizes the way that AES is. So actually, for some use purposes like this, it's actually not bad, because nobody would be expecting you to use it anyway. And security for security, bad idea, but it still works. So then let's skip down. The encryption itself, yeah, this is where we start to get into the nasty bits. So I've got a public key, I've got a message, and then I've got this label. And I've got, yeah, I'll skip past that. I've got this method, encrypt OAEP. Now, OAEP is a way of reorganizing an RSA packet. So, I mean, it is, when I said it's not possible to reorganize them in the same way it is with AES, it isn't. But there is this particular mode which scrambles the packet effectively and makes it much more difficult for people to figure out that it actually is an RSA encrypted chunk of data. And in this case, we're going to use a hashing algorithm to take care of that. And the one we're going to use, don't use. SHA-1 is not to be used for real world purposes anymore. It was cracked several years ago. It is not a safe and reliable hashing algorithm. SHA-2 is a relatively safe and reliable hashing algorithm, especially if you use sort of like 256 or 512-bit. SHA-3 still isn't standardized, and there are other hashing algorithms out there. Basically, all a hashing algorithm does is it's a one-way algorithm. It says, given a value, I'll find you a point in a very large space that I would stick that data at. But given that space in that point in that large space, I could never tell you what the data was that caused me to put something in here. So you can have many different pieces of data that would all go to that same point. And but SHA-1 is just not a particularly strong algorithm, not when used this way. If you want to use it for a HMAC, a cryptographically secure message signature, then SHA-1 is fine, because there's a whole pile of other boilerplate in that algorithm that it just cares that SHA-1 happens to be a way of scrambling data. So in this particular case, once we've done that, we've got our encrypted thing that's going to be squirted in the format and the wire. The decrypt is actually not really any different. We've still got to connect up. We're going to decrypt the message we get come in. Now you notice that here we've got our key, and that's actually our private key, which the other party has encrypted our message with, or rather for, with the public key that we've given them. We've got a message that we need to decrypt with it, and then we've got this same label served in this particular case that allows us to actually do that decrypt. And without that, the decrypt will just give us nonsense. And it's a parallel case. I mean, yet again, for doing the decryption, we need to descramble it from the OAEP format, but that's what we use the SHA-1 for. We've got some randomness involved in there, which is why we've got the random reader, and then we've got the thought of having 5 things as a parameter in a function in Go it doesn't happen often. This is the point at which we start to feel like perhaps we're programming in C rather than Go, but it's just the way it is. obviously we've got the inverse case. We now have to read data rather than write it. And there's not really a lot to that. I mean, to be honest, it's dull. One other additional thing we do have to have, though, is we have to load in our private key in the first place, so as to be able to publish a public key. Because otherwise, you know, the public and the private key, the cert file that contains the private key is what we actually use to extract a public key. So it's not like we have the public key lying around most of the time in another file. We can put it in a PEM file if we want, but I mean, it's then decoupled from the private key it's for. There's no guarantee that if I serve up a public key from a file that's separate from the PEM, that it's actually the public key I want for my private key. The other thing that we want to do in here is, obviously, when we're doing the connection in the first place, the other party says to us, I'd like to send you something. And we say, then here, have my public key. And we send them the public key. And then they've got the public key. And then they do something to send us back a message that's encrypted with that public key, and then we decrypt it. So I've introduced this idea send key, which actually wraps up the whole process of sending off that key and getting back a method. Now, loading a private key for RSA is slightly different than the example we saw with TLS. There, we just have to say the TLS library under the hood knows how to do all the loading. We just give it and we give it a key, and we give it for decrypting the file if necessary, and it just loads. But here, we're actually going to have to do a little bit of work with the PEM file, the actual format we get it in. I've used IOUtil for read file because I just want to read the file. I don't want to take it byte by byte, line by line. I just want to read the whole thing. And then I use the encoding.pem package to actually decode a PEM format file, which will give me back something if it's a PEM file. And then I check that the block type is RSA private key. Now, this is one thing I really dislike. When I check to see if it is actually an RSA private key, I'm checking that against a string value, and I don't like that. And for real world code, I would actually put my own wrapper around that, so that wherever I use it, I just check if it's got a property private key set or not, true or false. Whereas otherwise, I'm going to end up at some point either mistyping RSA private or key, and I'm not going to be able to load a key file. Anyway, in this particular case, I'm assuming that my key file is in a format called PKCS1. There's a whole pile of these public keys certificate standards or something. I can't remember offhand. But there's at least 11 of them, and they each define different file formats or different key formats. And we're back into territory that's actually mostly just the UDP code back there. All that send code is doing is actually wrapping up this whole idea of using a GOB encoder to allow direct binary transfer from one Go program to another. And for real world code, I wouldn't actually be using that anyway, so it would be a different pattern to this. But anyway, so well, the pattern would be the same, but it would be different structure for things in there for doing it. We'll skip all that. That's kind of boring. Okay, I'm going to wrap up with something that I've just spent the last 4 months obsessed with, and that is WebSockets. Because once you play with WebSockets, it's like, I really don't want to use any of the other methods for getting a connection. And the reason for this is WebSockets go straight into any web server. Now, that handle is willing to give you a connection back anyway. So this means if you want to build infrastructure and you want your infrastructure to be network agnostic, building it with WebSockets means that all you need on any endpoint that you're going to run a server on is port 80 or port 443 if you want to use TLS, or some other port if you want to bind your web server onto another port. But the point is, corporate firewalls nearly always leave port 80 open, meaning that if you want to use a firewall to tunnel a connection through to a box internally, and you want to be able to do TCP traffic rather than web traffic, so you get a live stream, WebSockets are the way to go. And that kind of changes a lot how you think about infrastructure once you can do that. So this is fairly quick. This is really quick stuff, actually. So firstly, I've got a couple of files I'm going to be serving. I've got a hello program in hello web page rather, and you'll notice I've got a script that's source is just the /JS on the server. So you hit that with a web request and you will get the JavaScript. And then I've got the JavaScript that's going to be served off of that particular URL. In this, all I do, and this is not the best way to do it because window on load I've discovered has awful problems with pre-caching in web browsers. But window on load will just go and run a function when the whole of the web page is loaded. In this particular case, my function is going to open a WebSocket, and I'm going to be serving on localhost port 3000 and on the actual URI hello. And all I need to tell JavaScript to make sure that this is a WebSocket is the ws://protocol mode. If I want to open a secure WebSocket with TLS under the hood, I would put an extra S on that. It would be WSS:// and it will take care of it. Once I've set up the socket, I'm then going to have a message handler. Now, normally you would have an interactive loop of some kind in here that would respond to messages coming down from the server and then trigger messages going back up in response, as well as having probably and you'd probably put the socket itself as a global variable in the JavaScript so that you could actually have other things in the page when their event handlers trigger could send things on that socket. Because every time you do a send on a WebSocket, you're sending a cohesive message. It's not packet oriented or datagram oriented, it's message oriented. And this actually makes it quite neat to play with, because whenever you do a write on it, you'll get a read of all of that you've written at the server end without you having to, it's great if you want to write chat clients and interactive monitoring tools and all kinds. Anything where you want a live connection, basically, and you want to multiplex lots of them together for given purpose. Database front end, if you wanted to just have expose a database driver, a raw Go database driver, if you wanted to, you could expose it over WebSockets, and each one could be handling a different web database connection. The sky is the limit on what you can do with them. And at some point, I plan to write a proper, detailed, sensible talk, having given one in Go Lab last year that was a little bit mad. Anyway, all we're going to do in this message handler in the JavaScript is we're going to, every time we receive a message, we are going to create a new div element, and we are going to append that to the body of the web page. Nothing more. Now, actually, we're only going to end up doing that once, because after we've done that, we are not sending anything back up to trigger a fresh message send. But if we sit there and the server decides that it will send us multiple messages, we will just print them out successively in the web page. It's the most boring sort of message board in history. That's what's happening that side. Now, behind that, we have some, let's get past that. Behind that, obviously, we've got a Go program. And a server for WebSockets is trivially easy to write in Go. This is something I really like. Firstly, I'm using IOUtil again because I'm going to set up a boilerplate function called serveFile. Now, normally, if you're writing a HTTP server, you would use, oh God, I've lost the name of it now, but there's a particular function, static content, I think it's called, or static file, or serve static. Anyway, it allows you to serve a directory statically. But I don't have any of these files shoved away in a subdirectory. I obviously wouldn't want people accessing this server to be able to download the server's code and all of that. So I've instead introduced this idea of a file that you can serve individually just by sticking it on a URI. It's not very exciting. It's got a handle func for the server. I set the content type, and then I print out whenever there's a request the content of the file. It's very dull, but it means that down here in the code below, I can now serve out both the files I want to, just as individual file serves. Yeah. I often write stupid little utilities like that in things as I'm going, and it's yeah. The meat of the program, though, actually relies on the standard WebSocket implementation that's currently in Go's experimental library support. Now, it's been there an awful long time, so I think it's solid. I've done quite a lot of playing with it over the last 4 months, and I haven't found it's a slightly weird API at times, but it's perfectly solid for doing work. Never once will you find yourself having to care about socket promotion or connection promotion or any of the other stuff that books on WebSocket will write about at great length without really telling you what to do over them. And yeah, it gives us this nice WebSocket handler. Now, a WebSocket handler takes a WebSocket connection handling function and wraps it up in a manner that looks to the web server like a standard web handler. So, you know, the web server is actually seeing for this route hello, it's seeing a function that takes the response writer and a request. But all I'm seeing as the person who's using that is actually a function that takes an actual WebSocket that I can just read and write on, because I don't care about the web aspect. If I need to, it is possible to get back to the raw request from the actual WebSocket connection object, but I don't care about that. I've got a WebSocket now. I'm talking one-to-one in real time with the server, sending backwards and forwards. I'm doing what people for years were trying to do with Comet and Ajax and long polling and all of that, only I'm doing it properly because I've got an actual TCP socket. And as you can see, sending data on one of these things is not particularly difficult. My send is literally as simple as that, websocket.json.send. I'm sending it in JSON format. Yeah, the assumption is that you want to use JSON for sending anything complicated over WebSockets anyway. So that's actually handled inside the WebSocket package. You don't even have to import encoding JSON to handle it. It's just assumed that that is what you're going to want to do. You're going to want your Go message translated into JSON. The more interesting thing, because I mean, there we're using JavaScript as a client. The great thing is we can use Go as a client for WebSockets. So I can actually open up a WebSocket connection from a Go program using exactly the same kind of pattern of code I'd use with TCP, only simpler. And shock horror, I end up with an interactive TCP connection, but without any of the annoying boilerplate to set it up. So here I just dial up the server with the request that I want. Now you notice there's 2 addresses that go in, and that's because I, as a client, I don't have to tell the server what my address is. But if I do tell the server what my address is, it can at least know roughly where on the internet I am. It can also check that. It gets access to an origin address that's normally set in the network layer. But if it's not set, then yeah. And the only thing I then have to do is just receive some data actually on the WebSocket. Now you'll notice here I'm doing this. I've got a string variable and I'm actually passing it as a pointer and reading into that pointer. It's being treated as a buffer. And that's because under the hood, JSON's receiving, well, it's receiving the JSON data, and then it's using reflection to figure out how to pack that into whatever type I give it. And that type can be arbitrarily complicated, obviously. So if you want to send around really complicated Go data states, you can, as long as they can be reflected or and then, you know, turned into JSON. And that covers that. The stuff on WebSockets isn't yet in my book. All the other stuff is in there. It's not very expensive. It's like $10. I've been writing it for 8 years. It gets a chapter every year on average, sometimes every 2, because I do an awful, I do a lot of research work, so I'm not always doing Go. A lot of my time I'm actually doing weird shit with Ruby instead. Pretty much the same weird stuff with Ruby, but weird stuff with Ruby. Obviously, if you've got any questions about any of this, I'm on Twitter. And apart from that, yes, I've got a slide share linked at the bottom. 54 decks at present, mostly on Go. Loads of stuff around crypto. That's it. Thanks very much. Now, how do I say? Oops.
Thank you very much, Ellie. That was great. Has anyone got any questions just while we're here? Let's see if anyone can write in the chat, or you can unmute yourself if you like.
It's all right. I often have shell-shocked audiences. I'm often a shell-shocked presenter, so I must admit, I was hoping that we'd all be out of lockdown by now, because I was looking forward to coming over to Belfast to give this.
Yeah.
And it is very weird giving talks remotely. It really is.
It is a bizarre situation we all find ourselves in. I think we almost needed a passport to get to Belfast now, Ellie. But that's another talk.
So I don't think I can. There's no import duties on me.
Smuggle you in somehow.
There might be on the way back, and depending on whether I can pick up a decent bottle of whiskey or not. But I mean,
yeah. Right. Has anyone got any questions for Ellie? I think it's fairly quiet there. No. No. Well. Okay. We'll wrap up then. Thank you very much, Ellie. That was fantastic, and thanks for taking the time out to chat this. I think it was really, really interesting, and look forward to seeing you sometime in person somewhere at some stage. Well, that was great. Okay, well, thank you very much, everyone. That was a great evening. 2 fantastic talks there, and just left for me to say, really, our next meetup is on the 18th of March, and it'll be with Roberto Clapis from Google. He's a bit of a security expert. Oh, James, have you got a? Let me see if I can. Have you got a question, James? I think they're saying they couldn't unmute themselves. Let's just check. James, where's James gone? James Rooney. Can't see you in the chat anymore, James. Maybe he's gone already. There's a question here for you, Alan, actually. If a junior dev can do a talk.
Yes. Me shout. Anybody can talk.
Yeah. So that's Marvin. Marvin's asking. Yeah, Marvin, if you just get in touch with Alan or Belfast Gophers directly, you can sort something out with you there. Great. Well, as I was saying, 18th of March is the next meetup. And we have a chat lined up from Roberto Clapis. I say he's a bit of a security expert, and also quite a keen chef if his Twitter's got anything to go by. But I think he's talking about Go when he gets here. So, okay. Thank you again to Ellie and to Matthew for the talks tonight, and we'll see you all next month. Thank you very much. Anything else you need to add, Alan?
I just dropped the group's email address in the chat there. So if somebody does want to talk or has anything they want to talk about, just info@belfastgophers.com.
Right. Okay. Fantastic. Great stuff. Well, thank you very much, everyone. Enjoy the rest of your evening or afternoon or wherever you are. And we'll see you all next month. Thanks again. See you later. Bye.